Okay, more polynomial graphs. Oh, back up just a second. Today's Tuesday, January 28th. Just say that for the video purposes. Polynomial graphs. That's what we did yesterday, but yesterday we looked at left in, right in. We just said the right in was controlled by the sign of the lead coefficient. We are going to draw some today. Left in controlled by the degree of the lead coefficient. And just be careful because sometimes we bury that lead coefficient to try to trick you. But you saw that yesterday and you weren't fooled. So no big deal. We are going to start drawing them today. Not technically perfect, but getting the roots right and the number of turns right. And so let's do a little bit of what we did yesterday. Let's look at these three polynomials. We looked at these briefly yesterday. X cubed looks something like that. I guess we should be a little bit careful. X cubed without anything would not have a dramatic wiggle in there. So I guess I should say it's x cubed plus some other stuff. X squared, we know what that looks like. And surely we haven't forgotten what his y equals x looks like. Just a line. Boring. Yep. What we're going to talk about today is how many turns a polynomial has. So how many times it changes direction. So maybe we should start at the easiest end here. How many times does y equals x change direction? None. 0 turns. How many times does x squared change direction? Once. Right? It's going down and then it changes to up. If it was negative x squared, it'd be flipped over, but it'd still have 1 turn. How many turns does x cubed have?
2.
I would say it has 2. It has 2. Well, is that enough for you to make a guess on the maximum number of turns a polynomial has?
No. There's
one less than its exponent. I'm going to shorten that up a little bit, but that's right. It's 1 less than its highest exponent. So the short way to say that would be degree minus 1. Degree minus 1. Now, we do have to be a little bit careful here. We have to say maximum number of turns because x cubed, without any extra stuff on it, you might remember, looks like that. And so it doesn't have any turns. So the maximum number of turns it can have is degree minus 1. But it might have less than that. Now, x cubed is always going to have 1 turn. X is always going to have 0 turns. But when you get to some of those higher powers, sometimes they have fewer turns than even degree minus 1. Let's knock out a couple of examples here. 3x squared minus 2x to the 4th plus 5. And we're going to tell its degree, max number of turns, and do a small sketch. I want to do several of these examples. So these are going to be very small, very inaccurate sketches, but we're going to combine some things here. Okay, so what's the degree of this guy? 4. Again, with the hiding the lead term just to be annoying. Degree is 4. So how many turns might it have? What's the max number of turns? 3. Now a sketch, I need it to have 3 turns, but I also need to use what we did yesterday. So what's going on the right end? It's even. That tells me about the left end. It's negative, so it's going down on the right. Even tells me it's doing the same thing, so I know it's going down on the right and down on the left. And I got to somehow sneak in 3 turns there. So let's see if this works. 1 turn, 2 turns, 3 turns. Like an M. So is that really what that graph looks like? Maybe, but we're just working on a sketch right now, right? We got to sort of build up to the exact thing. I know the end behaviors. I know how many turns it has. So it probably looks something like that. It's kind of as good as it's going to get for now. Y equals 5x minus 4 plus 6x to the 5th. You know what, why don't you see, it's only the second one, but you're smart people. Why don't you see? Okay, so let's see. What's the degree of that guy? 5. So how many turns? 4. What's the right end doing?
Going up.
Up. And the left end?
Going down.
Down. So right end is up, left end is down, and then I need to squeeze 4 turns in there. 4 squiggles. So 1, 2, 3, 4. And many of you had like symmetric, even-looking squiggles. Maybe that's true. Maybe it's not. We don't know enough yet. But that's a good enough sketch. All right, let's see if we can incorporate some more into our sketches here. Sketch a graph width. So we're gonna add some more stuff to it. Cubic. I guess the grammar there is not quite right. Sketch a graph with cubic degree, maybe. 0 at x equals 2. A max at x equals -1. Max, meaning like the top of the hill. At x equals -1. So that doesn't tell us like how high it is, it tells us where it is.
Oh.
That's a really good distinction, especially when we get into calculus, like where is the max versus what is the max. And a minimum at x equals -3. All right, that's a lot of information. Cubic, 0 at x equals 2, max at -1, min at -3. So this time I do need a... Okay, which of those things do you think I should use first? What would be the easiest to put on the graph?
Maybe the 0.
Probably the 0. So x equals 2, there's a 0. Let's see. At -1, there's a max. I don't know where it is, but because it's a max, I'm thinking up here somewhere. And there's a min at -3. So if that's a max, a min's, beneath that, down here somewhere. And then if it's a max, it looks, it's the top of a mountain. A min is the bottom of a hill.
I thought your minimum 2 is what?
Oh,
Minimum term.
a local minimum. That's a little bit different than an absolute minimum. That's a good point. So a local minimum just means it's at the bottom of a hill. It doesn't mean it's the lowest point on the graph. And then I see if I can sort of connect all that information with a cubic. And it looks like I can, like this, this, this. Something like that. That's a really good point, Jack. Though when we say max and min, we mean a local max and a local min. Just the top of the hill, the bottom of a valley. But it might not be the tallest hill, and it might not be the lowest valley.
So So those maxes and mins are just based on this group.
Yeah, and we don't know like how tall they are because it didn't give us that information. So our graphs could look different. Like you could have a graph that looks like that, and that would be the same, assuming my -1 spot still at the same spot. Right? That would still fit all of the requirements of that graph. So your pictures could look a little different on some of this assignment. And this one we specified a lot, so they're not going to look too different. But occasionally we can specify not as much and sort of leave it more open-ended. Let's see. This one we want an odd degree function. So what does that mean? Opposite, the ends will be doing opposite things. We don't know like which way yet, but opposite ends. Zeros at -1, 2, and 5. And a negative lead coefficient. What do you think we should put on the graph first? The zeros. That's definitely anchors. You definitely know where those points are. 2, 3, 4, 5. Okay, a negative lead coefficient. What's that mean? Right side down. So I can go ahead and going down off the right hand side, and the left side's up because of the odd degree function thing here. The left side is up, and then see if I can finagle the rest of the graph to hit the zeros that I want, something like that. It could have a lot more bumps. It could. I don't.
You got an extra bump right there.
It's possible.
But you're adding an extra 0.
Okay, now don't add an extra 0 because it told us what the zeros
I
are.
didn't add an extra 0.
But if your bumps are away from the axis. But I can still do extra bumps without an extra 0. So something like that. That would be a little bit crazier.
Or unless you did a bump where like -1 was the vertex. Could that work?
I don't think that would work because that would make it. You'd have to have. It would be going down the wrong way. Like you're wanting it to bounce at -1?
I'm just saying, like it could go, you could hit -1, come back up, go through 2, and then go through 5.
And you can't get another 0 in there because these are my only zeros.
Yeah, I figured it out now.
You could add some more bumps after you did those. Like you could add a whole bunch right there. So now, goodness. How about what power would this be? How many turns do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be an x to the 13th. But it still fits all the requirements. It's odd degree. It has those zeros, the negative lead coefficient.
It could be a higher one.
It could be higher. It could be 15, 17, 19.
13 plus.
13 plus 2n is going to be fancy. We can do our homework, but there's one more thing that we need to think about. So let's turn to the homework and make sure we hit a couple of things. So you can, mostly it's what we've just been doing. Draw a sketch of the polynomial described, some of the graphs, probably most of the graphs, can be drawn in more than one way, and some may not be possible. Well, that's not very nice. So, where are we looking at? What are you looking at first? Number 2? Multiplicity of 2. Okay, if a 0 has a multiplicity of 2,
That's plus 2.
an even multiplicity, this is like noteworthy, I should have put it on the notes. An even multiplicity, like 2 or 4 or 6, means your 0 is going to bounce there. Like that.
That means on the 0 to 2, it's going to bounce.
It's going to bounce.
I printed 2 of these. I don't know that we need them, but if you want to hold, I don't know.
I know.
That's all we know.
So even multiplicity bounces. That's not hard to remember because you know what x squared looks like. Especially just x squared. It bounces at 0. What does an odd multiplicity do? It crosses. It goes through. Now, if it's an odd multiplicity of 1, it just crosses sort of like normal, like a line. If it's a multiplicity of 3, well, you know what does y equals x cubed look like? It's got a little squiggle. So a cubic multiplicity, it still crosses rather than bounces, but it does kind of a wiggle through the 0.
Didn't we say earlier that the multiplicity is like a double root?
Mm-hmm. So that's a double root right there, and right there, and that's a triple root right there. So that's the connection between equations and graphs. We're not quite there yet, but this would be, well, I mean, you've seen this. Y equals x cubed looks like that. It has x equals 0 3 times. So it's a triple root at 0, and that's also what makes it do the squiggle.
It says 3, like in number 1, it says 3 zeros.
Mm-hmm.
Could you just draw that? See it?
3 distinct zeros just means put 3 zeros on there somewhere. Distinct, though, so they have to be different. A positive lead coefficient. So that would mean we're going up on the right. It's cubic, so we got to be going down on the left. And then we can just connect the dots in between there. Carefully, though, we don't want, for this one, we can't have the extra turns in there. Like on that last example, we were being silly and we had 12 turns or whatever. Why am I limited to 2 turns on this one? Because it says cubic. So there can only be at most 2 turns. So I don't get to go crazy with my pictures here. All right, A0 of multiplicity 2. So let's just pick one somewhere.
Does that mean there's only 1 0?
That means there's
You tell me.
more than 1. It says it's
Why is there more than 1 0?
imaginary.
They're on top of each other. Because it's the negative.
How many total zeros am I supposed to have?
2, 3.
3. That one's a double, so there's one more somewhere.
So does that mean that it goes through something?
It has to go back up because it needs to be opposite as well.
And be careful, the negative lead coefficient, at least the way I drew this one, means I've got to be going down at the end. But this is a bounce. So something like that. But that's okay. Now I can another turn and go up through that one.
What's the difference between 1 real 0 and 2?
Hold on a second. Let's stay on 2. There's a different way I could have done this. If I had put my double on the... If I said this was my double root,
It has to be.
then it would have looked like that.
But it says it has to.
Multiplicity of 2.
It says A0 of multiplicity 2. So that 0 has a multiplicity of 2 because it bounces.
Oh, that means it has
2, you have to bounce it rather than put it on the 2.
Correct. It doesn't mean a 0 at 2.
At-
Multiplicity of 2 means there's 2, it's a double root. Okay, now number 3, one real 0, 2 other complex zeros, a positive leading coefficient. Okay, one real 0. So how many times am I crossing the x-axis? Once.
In R.
So wherever you want to put it. 2 complex zeros. Let's see, a positive lead coefficient, so I got to be going up at the end. So, do you know?
Cubic, you just kind of squiggle it.
It's cubic, so it needs a squiggle in there somewhere.
Just gonna squiggle it where it doesn't hit the thing.
That's right. When it squiggles without hitting the thing, when it squiggles without hitting the x-axis, that means complex zeros. Right? Because you're getting turns, but you didn't cross the axis, so like something crazy is going on. There's zeros in there, but they're not real zeros because they didn't hit the x-axis. That's another one where I suppose we could have done it that way, and that would have been one real 0, 2 complex zeros, positive lead coefficient.
How is 5 is 4 real zeros, but it's still cubic?
How about number 4? Let's back up.
Yeah.
No real zeros, negative lead coefficient.
But you just don't. Oh, wait, mine
It's not possible.
Why is it not possible?
Because you have to cross the thingy. Opposite.
If it's a negative lead coefficient, then it looks like that. But if it looks like that, it's got to cross the x-axis somewhere.
Well, even if it's the other way, it has to cross the x-axis.
Even if it was, that's right. Even if it was a positive lead coefficient, you'd have to cross the axis somewhere. So that's not possible. An x cubed is going to have at least one real 0 because it goes forever up and forever down. So it's crossing the x-axis somewhere. Now, Jack, about number 5.
How do you have 4?
Yeah, 4
Oh, you can only have
Is that 2 double?
I don't think you can.
Well, if you have 4 distinct real zeros, what power would that lead you to?
4. 5. 4.
X. I guess I can do
But this is supposed to be a cubic,
that. So, yeah.
so that's not going to work.
That's not.
I'm just writing out possible. 2 distinct negative zeros, 1 positive.
Let's see if we can put all this on there. 2 distinct negative zeros. All right. 1 positive 0. Okay, so far so good. Negative lead coefficient. That means we're going down off that last 0.
That's easy.
Positive
A positive y-intercept. So is that going to work?
Yes. You have to
Yeah.
cross the line.
Because I will cross the y-axis on the positive side somewhere. I was worried about that one. What if that one had said a negative y-intercept?
That's not possible.
That wouldn't have worked. The things would just be out of whack. Okay, let's see. 7 I think is easy. 8's not bad. So why don't you try, I keep saying they're not easy, why don't you try 7 and 8? Instead of me working some. Why don't you work some? So yeah, there's 7. 8 has multiple possible answers. 12, probably, that's about the only thing you can make 12 look like. Number 9, 2 distinct real zeros, 1 0 with multiplicity of 2, and a negative lead coefficient. Okay, so 2 zeros and 1 0 that's a double root. And you don't have to label it on there, but I think it's helpful. That way when you go back to draw it, you know you need to bounce there. Multiplicity of 2 means a bounce. Okay. Negative lead coefficient, so I got to be going down at the end, but that's also a bounce, so there's my right end. Now let's see if I can make the rest of this work. Turn around, hit that 0, turn around to hit that 0. 1, 2, 3 turns. Negative lead coefficient. I think I'm good. So number 9. 9 you could have different answers for, because you could put that double root in different places. 9 you could put the double root in the middle. Or you could put the double root on the left. So it's just a matter of where you want your bouncy root. What'd you say, Cooper? 10? 2 real zeros, each of multiplicity 2. So two bouncy roots. Double root. Positive lead coefficient. So up at the end, but I've got to bounce. I can't go through that one. And then I've got to bounce off this one as well.
Would that not have an imaginary zero?
It does not have an imaginary 0.
It has that middle term.
It has a hump there, but it doesn't have, like, to get an imaginary 0, it's got to have like a more of a squiggle, not just a turn.
Okay.
Maybe 2 turns without crossing would be imaginary. Again, your assignment is the rest of this, so we get a little harder with quintic. 18 through 21 looks fancy, but if you look, what is 18 through 21 talking about? In behavior, that's just review from yesterday. So that's all your answers there, either plus or minus infinity. Just be careful, we like to hide that lead term. Which one?
17.
8th degree, goodness. 2 distinct, non-repeated zeros. Positive leading coefficient. Positive leading coefficient. It's got an end going up. So there's one turn. I'm not doing this on the graph because I don't know if this will work or not. So this is my rough draft area. 2 non-repeated zeros. And I need to end going up. And I can have 7 turns. So 1, 2, 3, 4, 5, 6, 7. So there we go. That is possible.
Or you could put all your terms below.
You sure could. You could put all your turns below. Yeah, you could go, so 1, 2, 3, 4, 5, 6, 7, like that. Yep.
So it can say it has less zeros in its degree, but it can have more zeros in its degree, right?
That's right.
All 3 positive zeros.
What did you say?
16, and as many distinct positive zeros as possible.
Like 80 degrees now, too.
So on number 16, how many distinct positive zeros can it have? 6. You just got to put them all on the right hand side.
Number 13.
Cody says 13's not possible. 5th degree. So they're doing opposite things. So yeah, somewhere you're crossing an axis, either heading up or heading down. So yeah, that 13 wouldn't work.
Are they both random infinity?
All right, so another worksheet that you can finish before you leave, I think.
Yeah.
Only 5 minutes left, but
Because it's
we're almost done.